Practice for you to do. Review everything chemistry. There are a couple of tricky ones here. It is off of Quest A+, so it's the practice diploma from 2017. The first question is just going over if you know photosynthesis and cellular respiration, which is reactions you want to have memorized. So going through this, just the statements. Number one, reactants are glucose and oxygen. Those would be products in photosynthesis. Number two, reaction stores energy in chemical bonds. This is true. The products are carbon dioxide and water. That is not true. Those again are reactants. And lastly, the reaction absorbs energy from the surrounding. This is true because it's endothermic. So the answer here is B. Now the second one gets right into Hess's law long. So we have a target equation here, and we have two equations we can manipulate. Now when you're doing this, taking a look at the first one, we have C2H5OH right here, but there's two of them. So with our enthalpy here, to make that match, we want to multiply this whole reaction by 2. And then the next, times 2. And then the next one, we see that we have C2H4O and C2H4O over here. But with this one, we have, for number 2, we need it as a product, not a reactant. So we're going to flip this reaction, making it positive. And then the other part here is that you have 2 of them in the target and only 1 in the manipulated. So we're going to multiply this by 2 as well. And when we're multiplying by 2, we definitely want to multiply everything by 2. And if you write this all out, you will see what you don't need canceling, and we will get the correct number of moles for oxygen and water. So when you add these together for Hess's law short by changing your sign and multiplying both of these by 2, you'll see that your answer is B. This next one, we are just taking a look. What do we have here? We have some information of calorimetry. So we'll have our formula NH equals negative MC delta T. And it's asking, what is it asking? The molar enthalpy. So we're solving for H. So it does tell us the amount of moles of what's being burned, which is methanol. It tells us the amount of water, but that needs to be in grams. We do know the specific heat capacity of water. And we get the final and initial reading of the temperature that we'll have to take the difference. So let's start to fill that in. So we have 0.0345, and this will be times H, and that will equal negative 100 grams times 4.19. And if we're reading our thermometer, your final reading here, it just looks like it from the meniscus, it's 1 over, so it would be 74 degrees. And over here, it's 1 under 21, but we're going up by 0.1. Oh, I did that wrong here. So this would be 73.1, just taking a look at the scale. So this one would be 20.9. So when we take the difference there, we are going to get 52.2 degrees Celsius. And then you'll see our units canceling nicely, isolating H, and we get 6.33.96. Oh, wait, this decimal isn't here. 633.96. Knowing that we also divided by 1,000 to get to kilojoules. And then when we want to be in scientific notation, we'll have 6.3. Before we can drop the rest, the 9 affects the 3, so round that to 4, times 10 to the power of 2. So this is 6342. Now when I did do this, and I was doing it very quickly, my original answer I think I put in, I forgot to round that up. So just be careful with your rounding and just take your time. Our next one, a student has equal mass of the following, and we have this chart. And then it's saying if we had the calorimeter, so the calorimeter is with these 2 experiments, or is what's being manipulated. We're changing what it's made of. And they're asking which one would undergo the smaller change in temperature. So the smaller change would be the ability to resist. So if you take a look at your specific heat capacity of aluminum, it's 0.897 joules per gram degree Celsius. And if you take a look at tin, it will equal 0.227 joules per gram degree Celsius. That means it takes less energy to heat up tin than it does aluminum. So the one that would undergo a smaller change in temperature would be aluminum, because it takes more change to heat it up, and it's because your specific heat capacity is larger. So just a bit of a theory question there. We have this example with the equation given, and it's asking in this one to convert to carbon as represented by the following. Oh, it looks like I cut off the question, but it's saying the answer is D. So it looks like this question's asking what is the molar enthalpy of either carbon dioxide per minute. Okay, so it's either asking the molar enthalpy of carbon dioxide or ethanol in this reaction. And I know that because I can see the answer. And that just means whichever one is asking, we would pull out the enthalpy. So this would be negative 58.4 kilojoules. And we're dividing it by 2. Because if we're looking for the molar enthalpy, we would want to see what 1 mole would represent, not 2. Number 6, the standard molar enthalpy of formation. In this one, we have that reaction that we see here. If we're doing enthalpies of formation, and it's asking for hexane, and hexane is this one here. So this means we don't know what it is on page 4 or 5 of our data booklet. So we have to use Hess's law short, and this is our unknown where we do know the reaction. So my short way of writing this out is delta H of the reaction equals the sum of the products minus the sum of the reactants. So if we start to use, and you would use page 4 or 5 to get the enthalpies of formation of these two, just be careful for the gas for water, because if you write down liquid, it's going to be different. And we also can fill this in for delta H. So you'd have negative 7,709.8 kilojoules, and that will equal your products. So 2 times that unknown value. Oh, that's not my products. My products are on the side. You'd have 12 times carbon dioxide, which is negative 393.5, plus 14 times your water as a gas, which is negative 241.8. So we'll get the sum of this, and then we're going to subtract our reactants. So we'd subtract 2 times our unknown value of that hexane. And then you'd also have to just remember that an element by itself is just 0. So this one essentially we don't have to account for because it's just 0. And so now we can isolate our 2x and divide by 2. So as long as we do the math correctly, you'll see your answer is D. Our next one here is just showing that we can balance. So we have our complete equation, but it's unbalanced, and then it tells us the molar enthalpy for this reaction is given here. So remembering that molar enthalpy is for 1 mole reacting. So we would go ahead and balance it, but when we're done, we want to definitely make sure there's only 1 mole of the C2H2. If there's not, we'll have to manipulate our equation so there is. So we can go ahead and start that. And we'll see that we already have 2 hydrogen on each side. So we can move on to carbon. We would put a 2 here. Then we look at oxygen. Oxygen, there's 5 total on the product side. So to have 5 total on the reactant side, you would just want to put 5 and then divide it by 2 so that we have that fraction in there. Right, hold on a minute, just making sure. And then when we're looking at this, so this is our reaction to make it fit our enthalpy. But notice here it's saying when our delta H is doubled, what would the coefficients be? So if we are doubling this value, that means we've multiplied this whole equation by 2. So multiplying by 2 means we have 2, 5, 4, and then there would have been 1 here as well, so 2. Our next one, we have our reaction, and we have delta H's for the formation of each of these 3 molecules, and then it's asking us for which would show the reaction of HCl with sodium hydroxide. So if you wrote out this reaction, hydrochloric acid plus your sodium hydroxide, you will get the salt NaCl plus water, but your water would be a liquid, right? Think of a titration, an acid-base titration. So with that, you would go ahead and write down those values, and this is already balanced. We don't need any more coefficients, and we're just writing the values how you see it from this table that we have. NaOH was negative 470.3. NaCl was what was given, negative 407.3, and water, you'll get this one from your data booklet, page 45, 285.8. Now you want to do Hess's law short, where delta H of the reaction is going to equal the sum of your products minus the reactants. We do all that work, you'll see your value for this reaction is negative 55.7 kilojoules per mole. And now the reaction that represents that, so we'd have, because it's negative, you would have that drop in potential energy, because this is an exothermic reaction. So we can already take these two away, and now we want to see which of these graphs represent. So it could be either B or D, but now you just want to look at what it's saying about your delta H, and it's going to be B because the delta H is a negative value, not a positive value. This next one, looking at which statement is correct. So what we would want to know is just looking between the difference between your reactants to your products. We can tell that this is an endothermic reaction because we're seeing that rise, and then we just have that activation energy in there. So asking a correct statement representing the enthalpy diagram above is it is endothermic. So we can take away these first two, and would require the reaction enthalpy to start it. What does it say? And would require more than the reaction enthalpy to start it. Let me just see here for a second. This is going to be D, because your reaction enthalpy is just between here. If we want this reaction to happen, we'll have to put more in there. This next one, we have some information about the forward and reverse reaction. So if it's telling us the activation of our forward reaction is less than our reverse reaction, you can kind of draw this, and it's not totally to scale here, but it's not to scale at all. The distance from your reactants to the top of the hill, that is the activation enthalpy of the forward reaction. The distance from the products to the top of the hill, this distance here, is 80. That's the reverse reaction. So here we can tell just by filling those values in that it's going to be exothermic, and the reaction enthalpy is the difference between your reactants and products, which will be 10. You are dropping, and it's also exothermic, so we know that value has to be negative. Moving on to the next numerical response. This one is saying to match. So enzymes speed up digestion without being consumed. A match is burned. A catalyst is used. Electricity from a battery, blah, blah, blah. So this first one, examples that model activation energy in a chemical reaction. So activation energy is energy you're putting in. So that would be like a match being burned and using a battery. Seeing examples of an alternate pathway, this is always referring to a catalyst, and enzymes are catalysts, and then this one actually says catalyst, so that would be 1 and 3. Okay, so we're starting to now move in to electrochem, and this is just being able to read our chart. So it's asking when we're taking a look at this, ordered from weakest to strongest for the reducing agents. If you're a reducing agent, you undergo oxidation, so you're losing electrons. So when we look at this, what would be losing electrons would be your metals. So your metals here are your reducing agents. All these positive charges over here want to gain. That would be an oxidizing agent because it would undergo reduction. So if we're ordering the metals from weakest to strongest, so we can already roll these out because we're not looking at the ions, you want to start with the one that reacts the least. So which one is reacting the least would have the most X's, which would be IR. Then we would just go in order, and the only one that shows that is A. Question number 11. If the metals and the ions were placed in a table of standard electropotentials, the half reaction with the highest positive electrode potential would contain the strongest blank, and when compared to the hydrogen half cell, this half reaction would be located blank. So when we're looking at this, if you are stronger, so this one's looking at, just going back to that for a moment, if the metals are placed in the table, highest positive okay, if you're highest positive, you'd be the weakest reducing agent. So you would also be if you're the weakest reducing agent, you're the strongest oxidizing agent. And then compared to the hydrogen half cell, you would have a higher cell potential, because if you were looking at page 7, right, it goes strongest OA to weakest OA, and then strongest RA to weakest OA. And if you're looking at cell potential, it's highest to lowest. So you're most positive to the negative. So when we're looking at the strongest in terms of half cells being higher on the table, you would be a stronger OA and a weaker this should be an RA. And then looking at positive, if you're looking at the hydrogen half cell is 0 exactly before it gets negative. This next one, during the reaction, the bacteria causes the nitrogen to undergo blank. As a result, the oxidation number of nitrogen will. So if we're looking at, and this is the reaction that we're looking at to answer this question, we have the incomplete reaction. So we have nitrogen going from, and if you assign your oxidation numbers, you have -2 for oxygen, which gives you a total of -6. So nitrogen would have to be +5. Over here it is 0. So nitrogen's going from +5 to 0. That would show a gain in electrons. So that would be reduction. And then the next part is asking the oxidation number of nitrogen is decreasing. So our answer there is C. The next one now is asking us to actually balance this half reaction. So if you go to balance this half reaction, you want to follow your rules of balancing. So you balance anything other, and this is obviously going to be in acidic conditions. So you balance anything, it also says it there just in case you didn't know, other than oxygen or hydrogen. So we'd put a 2 here. And then you add in water to balance out oxygens. So we would need 6 water molecules. Then you add in hydrogens to balance out those water. Sorry, you add in hydrogen ions to balance water. So we would need 12 hydrogen ions. And then lastly, we have to balance electrons. So currently there's no charge on the left hand or right hand side. And on the left hand side, you have a net charge of +10, right? 12 from the hydrogen ions and 2 from the ammonia. So we're going to add in 10 electrons to balance that out. So when we look to see what matches, that would be D. Looking at question number 14, going through this, asking what does not represent a redox reaction. If you are not a redox reaction, it means you don't have an OA or an RA. The easiest way to see that is by assigning oxidation numbers. So like going through this, we know that the first one will be, right, because we'd have 0, 0, then we'd have +1, -1. So we have something gaining, another one losing. So we can keep going through this, and I think the only one that doesn't work out, and I'll just skip to save some time, is number 3. 3, if you assign your oxidation numbers, nothing is going to be changing here. There's no change. So then when it's asking what's undergoing disproportionation, you want to look at your reactants and see if it's both your OA and your RA. So in this one, so we know that these two are not going to work. We're looking at equation number 1. Looking at this, we have an OA and an RA, so it's not going to be that. And then, equation number 5. Now I'm sorry, that's a 4. Just to emphasize this, chlorine is a 0 here. And just assigning oxidation numbers just for chlorine, so we can see this, we have -1 here. And within the KClO, it's going to be +1. So we have chlorine that's gaining electrons and losing electrons. So if your reactant is doing both, that's showing disproportionation, and that's going to be how you know. Question number 15 here. We have titration, gives us a bunch of information here, and then it's asking the question. So we have acidified sodium oxalate, and it's titrated with the potassium permanganate. So potassium permanganate would be in this, oh, sorry, this wouldn't have a charge once it's in there, would be in the burette, because that's what you're being titrated with. So asking in the titration, the burette would be filled with the potassium permanganate, and hopefully you did a lab on this, because it is our common lab to show in Electrochem. And then when you're looking at your Erlenmeyer flask, when you start to titrate, the color at the bottom would be clear. There's nothing in there. And what shows you the color change is you're adding in that purple color, because this solution is very, very dark purple. So as you add it in, and this is just a natural indicator, as soon as you don't have any more of the sodium oxalate to react, then one more drop of purple would cause it to turn pink. So this answer is going to be C. The next one, I believe, is actually doing the calculation. So if we had that balanced chemical equation and we know it's reacting, and then we want to figure out the concentration. So we have all the information we need about the permanganate, and we want to find the concentration of the sodium oxalate given what we have. So we're going to start with that we know based on what we're seeing here. So just looking at what's reacting, your final burette reading is 26.2, and we're going to minus the initial burette reading, which is 6, and then that's in milliliters. You need to change that to liters. So we're going to start with 0.0226 liters of the permanganate, and then multiply this by the concentration, which is given. So multiply this by 0.02 moles per liter of the permanganate. Then you're going to use your mole ratio to turn your moles of your known into your unknown, and that's a 5/2 ratio. And then lastly, you're going to multiply by, or essentially divide by, the amount you're titrating. And every time you're titrating 10 mils, but that needs to be in liters. So we do all of that work and you get this value 0.113, then that would be your concentration moles per liter. But we want it in scientific notation. So just moving your decimal over one place, this will be 113 to the power of -1. Okay. This one we have some information about an indicator that is commonly tested. It turns blue to contain if you have Fe2 positive, and in phenolphthalein it will turn pink if you have OH negative. Okay, so we're using two indicators. So we had a setup of an experiment, and then the first question is asking what equation would represent the reduction half reaction in number 4. So if we look at number 4 here, your reduction half reaction, iron is wrapped. If it's reduction, you are going to gain electrons. So reduction is going to gain here. Looking at here, we will have wrapped in chromium wire plus water and that. Not that. So probably be the one with just taking a look for a second. I'm just taking a look, just kind of by process elimination. If we have iron nail wrapped in chromium wire, those are two solids. So just based on that, it can't be any of these because we need a solid present. So we also have water and O2 present, and reduction is gaining electrons, so we're showing that. Looks like the only option really there could be D, and that's without even looking at our data booklet. The next part, though, asking about colors and how we're reacting in the Petri dish. The pink ones, so if you have pink, it means you have to have that OH ion present. And when that reaction takes place, you'll see that OH ion will be present in number 2 and in number 4 because we have those reduction. And the other part, to have blue or pink, you have to see the Fe2 positive ion being present. And that will happen in reaction 1 and 3. Okay. And I definitely could go through that in more detail. So if anybody if you're watching this and you've made it this far and you would like more detail, just let me know. But I am just kind of trying to fly through it. Now, this next one is we have a reaction that happens at the anode and the reaction that happens at the cathode. So it's asking if when the reactions, we're looking for overall net reaction. So when you add these two reactions together, what will be the lowest coefficients? So you just have to remember, because it is electrochem, that to add reactions together, you have to balance electrons. So this first reaction needs to be multiplied by 3. And then when you look at what could cancel and reduce, you'd see your coefficients will be 3 for water, 3 for hydrogen, and 6 electrons are being transferred. This next one about standard electron potential, we would take a look at what's reacting based on what we see as our strongest OA and strongest RA. So your strongest oxidizing agent undergoes reduction. Reduction happens at the cathode. So these two would be what we have at the cathode, and that has a potential of 0.14, meaning these two are at the anode, and that has a potential of 1.66. And whenever you calculate your cell potential, you want to take your cathode and subtract your anode. So take this value and subtract this value, and you'll end up with positive 1.52. I'm looking at another cell and asking about the reducing agent. Reducing agents undergo oxidation. Oxidation is a loss of electrons. And then looking at the oxidation number of the oxidizing agent, if you're losing electrons, you would be decreasing. So your answer here would be C. I'm sorry, I said that wrong. If you're losing electrons, your number would be getting more positive. So it would be increasing. The next one, during the operation, the nickel electrode acts as the blank, and the color of the nickel electrode solution becomes. So if you're looking at your nickel electrode and we take a look at your data booklet and what's reacting, you'd have copper 2 positive with copper solid, and then nickel 2 positive is below it with nickel solid. So your copper 2 positive, because it's higher than nickel solid, is your strongest oxidizing agent, which happens at your anode, and then nickel is going to be at your cathode. So going through this, as the cell operates, the nickel electrode is your cathode. Did I say that right? So as the cathode. And, yep. Strongest OA as the cathode. And then the nickel electrode acts as the cathode. Yes, strongest is your oxidizing agent. Yep. Okay. I don't know why that's giving me so much issues right now. And then the color of the nickel 2 electrolyte solution. If this is at your cathode, that means your nickel 2 is getting used up, so it would become lighter. So this looks like your answer is D. Okay. Number 8. I'm looking here. That's what was throwing me off. I had a different one there. Looking at number 19, it's asking during the cell the species that is being reduced. So we can go back here for a second, just when we set this up from our data booklet. If you are being reduced, you are undergoing reduction, and that happens at the cathode. So nickel is being reduced, and the cathode always gains mass. So it looks like here we have copper, and copper is going to increase in mass. Okay, our next one, we have this information about pennies having 95.5% copper, and then later on only 4.5% copper. That's great. That's a bit useless information, but over here it's asking the time it will take to plate 0.106 grams of copper onto steel using this current. This is just showing we know Faraday's law. So using moles of electrons equals your amps times your time in seconds divided by the constant. And here you are solving for T. So you do have one extra step here because we have moles of copper, so 0.106. We're going to have to multiply that by your mole ratio. I'm sorry, your molar mass. So 1 mole of copper contains 63.55 grams. So here grams cancel, and you'll be at moles of copper. Then we need to multiply that by 1 2 moles of electrons over 1 mole of copper, so that we have moles of electrons. So we'll do that. And whatever value we get here will be on the left-hand side of this equation. You also have your amps, 15.0, so that will go in for the I. You have Faraday's constant, and if you don't remember it, it's in your data booklet. It's 9.65 times 10 to the power of 4, and you're going to isolate T. Remembering that T is in seconds, and when we are done, we should see that T is 21.5. Okay. Looking at these two questions with half reactions, when it's asking about the oxidizing agent in this overall reaction. So we have the two half reactions. What you want to take a look at before we actually answer this question is the order this is given. So even though it's saying half reaction and half 1 and 2, if you went to go place these in the data booklet, this one would be higher up. So this value, because it is more positive, would be higher on the table than this second one. So just knowing where we place it. So because it's higher up, we have that OA over RA. This one higher up becomes your OA. This is going to be your RA. Well, over here will be your RA. So that's the first part we want to do. So just knowing the oxidizing agent, because of that, is going to be A. So be careful with that, because if we don't realize that this is not given an order and you don't change it, you'll get that wrong. And then the voltage. So being the voltage, now that we know that, your voltage is still going to be for cell potential, your anode, I keep saying that backwards, your cathode minus your anode. So if this one is higher up on the table, right, than this one, then this being your oxidizing agent happens at the anode. This value gets filled in for A. This one would be lower at your cathode. That gets filled in for C. When you subtract it, you will see your value will be B. Okay, again, I know I'm going fast, so if there's any question you would want me to redo for you, just let me know. Then the next one, which of the following species could reduce COQ to COQH2? So in this one, you're just again looking at placement on the table. If it can reduce this, and we know that this is an OA, so to be undergoing reduction, you need a value lower than this on the table. So if you look at your values, silver is 0.8, that's going to be higher. Fe2 positive is negative 0.45, that could probably work. Then Pb is negative 0.13, and iron is plus 0.34. So just looking at this for one moment, which one could reduce this to that? Which, oh, being those are negative, this one's positive. I think I had that one written down wrong. So I think our answer here, well, I know it's C, but just to double check, knowing that these values are still larger, so we have to still get one below, and we'll get the one that is negative. Moving on to your organic section, and again, thank you for staying with me this far. So we're halfway through here. So going through the organic, talking about the acid that could cause the bromine solution to rapidly become colorless is. So this one is showing that when you add bromine, right, if you add it to a double bond, the color will go away. If you add it to everything that has single bonds, then you only have a substitution reaction on an addition reaction, and the color remains the same. So the one that would make it colorless would be the ones with the double bond. So looking at C or D, and that's because of the double bond, we have something that is unsaturated. So your answer was D. So that is just kind of your reminder to just make sure you know the bromine reaction. Breaking a double bond, color goes away. Single bond, you just get the substitution reaction. So question number 24, showing we know organic compounds. I can see here that carbon monoxide is not organic, HCN is not organic, and anything with a metal is not organic. So double checking A, everything there is organic, so that one will work out. Question number 25. So you have butane, and then it's asking the number of carbon-carbon bonds. If you drill butane C4, we would see that we only have 3 carbon-carbon bonds. And then the fact that you have, if it says H10, each of these carbons, let's just make this go away for a second, and that. Each of these carbons contain a hydrogen. There's 10 of them altogether. So that would mean that we are not unsaturated. If we were unsaturated, we'd have a double bond. We are saturated. And another way we could talk about that is just saying alphilic. Let's go a little bit faster because I don't want to lose this here. Talking about some qualities. Because you have an alkane, it is nonpolar. So number 2, it is a straight chain molecule because we don't have any circles going on. So not that. Lower boiling point than ethane. Note there's more carbon, so it would have a higher boiling point. It also have a higher boiling point than propane. And lastly, it can undergo substitution. And addition. It could undergo substitution, but not addition because we don't have a double bond, but it can definitely undergo combustion. So this is 2, 3, 6, 8. Number 26, talking about fractional distillation. So if you're looking at fractional distillation, you definitely have to know that it's separated based on boiling or melting points. I would say boiling points because it's usually just all gases. And then the heavier molecules are on the bottom. So this is definitely a question that I had to go back and reread just because of the wording. So saying here, compared to the number of carbons collected at the bottom, the number of carbons collected at the top would have a less boiling point. So for me, this one was just a reading question. That's why I got it wrong. But the answer is D. Going over here, the compounds above that are isomers, go through each of these. I would suggest drawing them out and then counting. And we would see that number 1 ends up being C9H18, so it doesn't work. Number 2 is C9H20, and number 3 is C9H20. So I just have quick line diagrams to show that. So I'm just looking here that my answer is 2 and 3, so it's C. Okay. Here, this question, we're just comparing boiling points of molecules that have the same amount of carbons, but then we're changing a few things. So, and that's happening with each of these, and then you can see a trend. So looking at this, when we're comparing them, the double bond, the first one saying double bond increases that boiling point. So if we look at that, this is a single bond, double bond. The boiling point is, is not getting higher, it is getting lower. So it has a lower boiling point because double bonds are easier to break. Triple bonds do increase it. As you see, a triple bond is higher than what you're starting with, and that's because of that linear structure that triple bonds will start to make. So 2 is one of our answers. Double bond decreases the boiling point. We just talked about that. Triple bonds do not decrease. Number 5, functional groups increase. As soon as you put an OH on there, you get a higher boiling point, as we see. So that is true. Chloral functional groups increase boiling point, and that's also what we're seeing is true. And then the other 2 show that that's going to work. So that was 2, 3, 5, 6, and that's like a very good theory question when it comes to boiling points. Looking at our compound about vitamin E, we can see that we have aromatic because you have a benzene ring, so it's not going to be C or D. And then asking about the functional group that you contain. Here it looks like, so we have carbon, what do we have? So we have a hydroxyl group. I think that's all we have. We just have this hydroxyl group on it. So it's B. I was looking at the ester linkage, but we don't have one. It kind of made me look there for a second, but that's not an ester link. Okay, so moving down to this one, we have our compound, and then we have 2 new compounds. This one, because we do have water here and a double bond forming, that is going to be an elimination reaction. And this catalyst you see above is just going to speed up the rate of the reaction. It won't do any shifting because it's not in equilibrium. This one, taking a look, the ester represented by the line diagram above. Here we want to see that the part that was connected only to that double bond to oxygen, that comes from the carboxylic acid. The part that's connected only to the oxygen, that comes from the alcohol. So the only part here that can work is going to be B, right? We have a propane with an OH group, so propanol. And then this part, we have those 4 carbons with our carboxyl group. Number 11, showing some reactions. The first one, the hydrocarbon combustion. So with combustion, you need oxygen producing carbon dioxide and water. This is number 3. Substitution, we are swapping out some molecules, but we have the same amount of reactants as we do products. So that would be number 1. Something that is inorganic. Here, inorganic, it looks like that is number 3, because we have carbon dioxide as inorganic as a product. Above with the inorganic reaction is that. And then the addition reaction, we need to break a double bond and form 2 new products, and that looks like, or not 2 new, we're adding on to the molecule, and that looks like number 4. Just want to double check here, inorganic. Okay, and I might go back over this in a second because I do have number 2 written up here, but here, NH4, oh yeah, this is inorganic because we don't see carbon. That's why. Here, we do produce something inorganic, but we start with organic molecules. Okay, question number 31, going through it, type of reaction we form. So when we're looking at the polymerization of the above reaction, to see this reaction forming, we do have an O coming close together to OH. So it looks like we do have water being formed, and anytime so that water is going to be formed, that means we have a condensation reaction and not an addition reaction. And the inorganic product is... so I have B listed down because we don't have carbon, and we can't have hydrogens as being part of our halogens, I think. Again, I got to double check. See, these are a couple that were definitely throwing me off, but once you kind of think about it a little bit more, I think it's okay. So now we're moving into the last section which is equilibrium acids and bases. So here just showing that we know how to read these equations. So we have products over reactants, and the numbers that you see as exponents are the coefficients, and then you just add the rest together. So then the one that works out here is going to be C. And the reason why this one was a little bit tricky, so for me, I originally put A, but A is not balanced. So to be balanced, we do have to add in some water, but remembering that water is not part of the expression. So this was a bit of a tricky question, so that's one to look out for. This next one here, we have this reaction, and then it is asking, what is it asking here? Blah, blah, blah. Oh, it's got cut off, but it does ask if it's heated, what would happen? So if you are heating the reaction, you are going to shift to the right, and I believe it's asking you about the Kc value. So if you are shifting to the right, okay, I'm just looking at this. I wish I had that properly. The concentration of that will, what are we looking at here? This doesn't help me if I don't know the number, does it? Not the best one to do. 33, I have the answer is C. And it would decrease. Okay, let me go back to that because I definitely need the question there, and without it, it kind of means nothing. So I'm sorry about that. Question number 12, the equilibrium constant for the reaction above. You are just filling this out. So you write out the Kc expression, products over reactants, and fill in these values. We don't need any exponents because everything is a 1-to-1, and you'll see your value here is 1.96. Now I'm really sorry. I wish I could go back to the last one, but we'll keep going. Just kind of going back here for one moment just to point out something that usually would come out. If it is asking you about a temperature change, that is the only thing that could affect Kc, right? So temperature could affect it. If it asked for a pressure or volume or concentration change, that does not affect Kc. Kc will stay the same. If it is a temperature change, in like this case, if you add in energy and you shift to the right, Kc will increase. If you cool this down and you shift to the left, Kc will decrease. So if you get more products, Kc increases. If you get less products, Kc decreases. And if it's not a temperature change, Kc stays the same. Okay, now this next one, we have a system, and then it asks an increase in pressure on our system. What would happen? And then because the slow decrease in system volume would. So in this question, we're going to, if you have a temperature or volume change, so an increase in pressure would be a decrease in volume, and then you would shift to the side with less moles. So you would shift to the left, and it would increase the number of moles. So when we shift to the left, that means we are going to make more of the methane. So we have our answer in A. So we're not shifting right. There is a shift, so that's not right. And reactions do not get faster or slower because there's no catalyst. Or, sorry, catalyst was not added. Okay, this next one is an ice question. So we have our reaction, and it's asking in this, what is the equilibrium constant of H2 and the concentration of H2S? So if you set up your chart, your initial concentration of each of these, so we had 2, 4, 2, 4. We have our mole ratio changing. So when you take a look at this balanced chemical equation for ice, so that was I, and then C, and then E. Your change is based on the mole ratio, so minus X, minus 4X, plus 2X, plus 4X. So I always say, like, for the negatives and positives, remember reactants are used up, products are being formed. So at equilibrium, we'd have 2 minus X. But for this one, it tells you it equals 1.25. So we can solve for X, and X will equal 0.75. Now that we know that, we can plug in for X. So the next one, 4 minus 4 times 0.75. And the last one, 4 plus 4 times 0.75. And if you see this and do it correctly, you'll see your answer is D. Okay, question number 36. So we have our reaction, and then it's asking the change of concentration of what is happening in our question here. So what do we have here? Number 13. Sorry, I was just reading the wrong thing. Okay, I have the answer is A, but why do I have that? I believe it was another ice question. So we have the flask. Okay, I'm just going to set up the ice question, and it tells us if it was ice, our initial of the first one was 0.430. The second, a mixture containing this and this. So that would be the same for both. It was sealed and asked M reach equilibrium. So this would be minus X plus 2X. And then we see the sketch below. So at equilibrium, you know N2O4 is 0.491. And NO2 is 0.0475. Because we're making this, I'm going to add this, and because we're using this up, I'm going to subtract this, just approaching it from the other direction. So doing that, I was just asking our final, the concentration was this, an initial concentration of C2O4. N2O4. Okay, hopefully I can just do this one quickly. So I'm just thinking about it because I have my whole page crossed out, and then just have that the answer is A, N2O4. Which means I probably figured it out on a different piece of paper and left it. Okay, just for the matter of time, I'm going to skip this for now, but I do know the answer there is A because I did check all the answers. But I need to go back and figure out why. So same thing, if you get stuck on this question, you would like me to make another quick video, I definitely can. Oh, I see, it says see next page. So what did I write out? placed in, used from approaching from the right. Oh, I see. A mixture containing that and, oh, okay. This, oh, sorry. This is, we don't know what this was. I read it wrong. That's probably what I did on my first page. So we want to know if it's the original. We have to use this bit of information, and this is right. It is being used up, so we are subtracting it. So we know that 0.430 minus 2x equals 0.0475. That allows us to find x, and x is going to equal 0.191. So that is our first part, the change in the concentration. So if they're asking about the change, they're asking for x in the first one. And then once you know x, and if we say y plus x equals 0.491, and you know your x value, you'll see that your value is going to be A. Okay, so again, I apologize for that, but I'm glad I figured that out, and it was just, again, my reading questions. Okay, question number 13, you have some information, and then you need to match. So the terms with the correct position. Okay, so we have our reaction here. We want to see that hydronium is being produced. So this would be a Ka value, not Kw. What's the next one? The concentration of X. Oh, in this expression. So the concentration of X would be, because it's products over reactants, would have to be one of these two. So I could say that this one is products minus reactants. I'll say that one is 3 for X. So, and then number Y would be 5, and Z would be number 6. Now with this one, just going through it for 1 second, they would have to allow 2 numbers because we could write this in either order and it would still be the same in terms of that expression. Number 37, which of the following stresses would increase the amount of products produced in the forward reaction? So if we are increasing products, we want to shift to the right. This would not do it because that would add in H3O. We would be shifting to the left. Catalysts do not shift the system. Increasing the pressure of the system, we would move to the side with more moles. Sorry, less moles. So that won't work. Increasing the concentration, well, that is definitely your answer, is D. Number 38, which of the following would be identify as a Bronson-Lowry base and its conjugate acid-base pair? If you're a base, you will accept a hydrogen. So when we're taking a look at this reaction, this is going this way, that has to be a base. When we look at this side, this is an acid, that would be accepting the hydrogen, that has to be a base. So we're ruling out these last two. And then your acid-base, conjugate acid-base pair means you're in a difference of just 1 hydrogen, but everything else would be the same. So that shows us it's A. Number 14, looking at the Kb value of this reaction. If it's Kb, we would look at our data booklet for this value here as a Ka. And Ka, it would equal 5.6 times 10 to the negative 4. So finding Kb, you take your Kw and divide it by your Ka. If you're plugging it in and not getting the right answer, just make sure to keep your Ka in brackets just because we have multiplying by that exponent. And you will see your answer is 1.8 times 10 to the power of 11, negative 11. So this would be 1811. Over here, looking at some trends about Ka and Kb, matching the species. The one that is amphiproduct, so to be amphiproduct, you have to be able to donate a hydrogen and accept a hydrogen. So that looks like it is number 2, right? We can donate this hydrogen and accept. The species that is a conjugate of C4H3O5, so this one, we're looking for a difference of just 1 hydrogen. So looking up for that difference there, could be number 3. I feel like we could put number 1 too. The species Oh, because it's conjugate base. So to be a base, you're accepting a hydrogen. And that would be the one that we're looking at. This B set is a conjugate acid. That would be number 1 because you want to donate a hydrogen from it. And the base with the weakest conjugate base is numbered. And the weakest one here, if Ka is increasing as you go up, that would be like reading your table, that your strongest acid is at the top and the weakest acid is at the bottom, where the opposite, your strongest base is at the bottom and your weakest base is at the top. So your weakest one there is going to be number 1. Number 39, which of the following correctly identifies that in a Bronson-Lowry neutralization would most readily donate and the one that would most readily accept? So here you have 2 that can donate. So I would say species number 1 would most readily donate. So taking out those last 2. And then the most that would readily accept, I would go with species number 3 because you have 2 areas that can accept. And so your answer here is B. Number 40, we have our example, and it's benzoic acid. It gives us some information that we have 0.070 moles per liter. And then the question is asking about concentration. So benzoic acid is a weak acid, meaning very little bit of product forms. So you would have a lot greater concentration of the benzoic acid than you do of its ion because we don't get much forming. So this is B. 41, this is number 16. We're looking to find the pH of the solution. It is a weak acid, so you have to use the Ka formula, which is a hydronium ion concentration squared divided by your weak acid minus hydronium. If you are finding hydronium, you can ignore this in the denominator. So we know the Ka, you can get that from your data booklet. You know the weak acid. You need to find hydronium. Don't forget to square root it to get that value. And then once you do that, then to find the pH of the solution, you're going to take the negative log of the hydronium concentration. So if we do that all correctly and answering with 2 sig digs, you'll get 2.68. Going just a little faster again here, comparing the carbonate ion, carbonic acid to benzoic acid. It's going to be a stronger acid because it's higher up on the table. And then comparing the hydrogen carbon ion to the benzoate ion, it is going to be a weaker base because it's higher on the table than what it's asking for. Here asking how your pH is changing from 2 to 5. How will the hydronium ion concentrate change? Every time you move up 1 on the pH scale or down, you're changing by a factor of 10. So if you're going from 2 to 3, you're timesing by 10. Times by 10 again, and lastly, times by 10. To get to 5. I hope you know what I'm getting at here. So you are changing by a factor of 100. And then the pOH of the solution. So if that's from 2 to 5, then looking at pOH, we can just subtract by 14. So we were changing from, if you subtract by 14, 12 to 9. So that would be D. Number 43 here about a buffer. A buffer of the solution will be made by mixing equal amounts of the acid and a solution containing. So if you have citric acid and you need a buffer, you need the weak conjugate base. So the weak conjugate base there is either C or D, and then asking when a small amount of the acid or base is added to the buffer, what would happen? So if a small acid is added, the buffer would resist a change in pH because that's what buffers do. We have that little bit will react with the opposite, just resisting that change until it can't. And then this very last question here, we have a pH curve. We can see that we have something that is polyprotic because we have not 1, but 2 equivalence points. So asking about this on the titration curve, the hydronium ion concentration, H3O positive, is less than the hydroxide ion concentration at the regions labeled. So looking at this, we want to say if you have is less. So it would be less when the pH is greater, because that means we have more hydroxide, and that is going to be at number 10. So we need the pH greater than 7. And then lastly, about thymal blue, what would be if in the determinant of the thymal blue indicator to identify, okay, both endpoints. We want to show that we do have more than one. Oh, wait a minute, but that one would only show that last one and not before. So we would need more than one indicator. So I hope you found this helpful, even though I was kind of going back and forth. Again, if there's anything you want in more detail, let me know. But this is a good review, especially if you are rewriting that diploma coming up here, or writing it for the first time if you didn't. And if you are doing that, best of luck on that. And if there's any other video I could do, just let me know. If you did find this helpful, please subscribe. And again, good luck if you're writing that diploma this week.